In this video, we're going to look at how the different sublevels have different energies. And we're going to start by thinking about electrons in an atom together. So electrons are both negatively charged, and so they repel each other. And if you're talking about electron and a proton, they're opposite charges, so they attract each other. And we want to know how much energy we have for attraction and repulsion. And so for that we have Coulomb's law and Coulomb's equation. This is not an equation you'll have to memorize, but an equation you'll need to know how to use. The different terms is that we have this epsilon naught is a dielectric constant. It basically tells you how well a medium shields electric charge. For Gen Chem 1, it'll be a constant I give you. Q1 is the charge on an atom, minus 1 electron, plus 1 for a proton. Q2 charge on atom 2, and R is the distance. So if you have the same charge, both negatives or both positives, your E is positive. You don't want positive energy, so your atoms or particles will repel. While if they're opposite charges, one positive, one negative, E is negative, that's good, and they will want to attract to make the E more negative. And the strength increases with increasing charge. If you have bigger numbers for your charges, your energy will have more repulsion or more attraction. So let's see if we can understand how to use Coulomb's law. So here I have 4 different interactions. And I just want you to see if you know which one will have the highest to lowest potential energy. So take a second and do that. Alright, so the molecule that's going to have the lowest potential energy, or most negative, is B. You have a big charge and a negative charge only separated by 100 picometers. And then the molecule that's going to have the second lowest is A, because it's plus 1, minus 1, 100. Then D, because it's the same charges but separated by 200. And finally C, you have 2 positive charges, so you get a positive number there. So that is your highest potential energy. So it goes B, A, D, C. Alright, so coming back to electrons in an atom. If you're an electron in a multi-electron system, you have 2 competing forces acting on you. One, you're being attracted by the nucleus because it has a bunch of positive charges, but you're also being repelled by the electrons that are closer to the nucleus than you are. And so you would say that the electron out here is being shielded by the nucleus, or from the nucleus, by the 2 electrons right here. And so the electron on the outside is only feeling roughly a plus 1 charge from the nucleus that is plus 3. That's the effective nuclear charge. Because the nucleus is plus 3, each electron is minus 1. We have 2 of those, so the net charge on this electron is plus 1. So it's being shielded with an effective nuclear charge of plus 1. Now sometimes electrons from outer shells can move into the inner shells so they can feel the full charge of the nucleus, and that's called penetration. So you can imagine that this blue is just a field of negative charge, and sometimes the electron can get enough energy to penetrate that field and be right next to the nucleus. That is what is called penetration. And if we look at radial distribution functions for different orbitals, we can see this penetration in action. So if we look at 1s, you can see that the electrons are always near the nucleus. That's what this x-axis is, distance from nucleus. 2p is always going to be somewhat far from the nucleus. 2s on average is even farther, but sometimes 2s can penetrate into the 1s. That's why you have some probability in the 1s region, but the majority of the probability is not. So shielding is a rare event, but it can happen. And since 2p can really never penetrate all that often, it has some probability down here, but much less, we say 2p is more shielded than 2s, because 2s can sometimes sneak into that 1s orbital. Now, what does penetration and shielding mean for energy? This means if you have different L quantum numbers, you're not degenerate. That is, 2s and 2p do not have the same energy. And this can also lead to things in higher principal levels having lower energy because they can penetrate. So 4s can penetrate easier than 3d, so 4s is lower in energy than 3d. However, once you go higher than 4s, really penetration is non-existent for everything, and all these quantum numbers start getting the same closer and closer energy, because remember, energy is dictated by Coulomb's law. So let's take a look at this. Here I have a energy chart for a bunch of different sub-levels. Remember, low energy good, so 1s the lowest, high energy bad, which is 4d. And if we're working with putting electrons into these orbitals, we have certain rules to follow. First is the off-ball principle, which says we always put electrons in the lowest energy orbitals before we put them in higher energy orbitals. Then we have Pauli exclusion principle, which says only 2 electrons per orbital, and they have to have different spins. And Hund's rule says if I have orbitals that are the same energy, like 2p, I have 3 orbitals, I'm going to put an electron in each of the p's before I pair up my electrons. So let's actually see what this means. Imagine I have 8 electrons. So according to the off-ball principle, I'm going to put 2 in 1s first. So 1, 2. And because of the Pauli exclusion principle, one electron has to be spin up, the other electron has to be spin down. Alright, so that's 2 of my 8 electrons placed. Now the next 2 following off ball has to go in the next lowest energy. 1, 2. Alright, that's 4 electrons. I have 4 to go. So my next energy level that is lowest is 2p. So I'm going to place my 4 electrons here. And to begin with, I'm going to follow Hund's rule that says an electron has to be unpaired first. Now I'm putting them all spin up. It doesn't matter if they're spin up or spin down when you place them in there. So I have one more electron to place, and I have to place it in one of these orbitals. Does not matter which one I place them in because they're the same energy. All that matters is that it has a different spin, so it's spin down. And so that is what my orbital diagram looks like for 8 electrons. And here I'm showing orbital diagrams for a ton of electrons, a ton of compounds. So you can see the different rules, off-ball, Pauli, and Hun in place if you go from 1 electron working your way down. I also have the notation for how to write these electrons, and we have shorthand. So let's look at neon. Neon is 10 electrons, so it's 1s2, 2s2, 2p6. Then we have sodium, which is 11 electrons, which is 1s2, 2s2, 2p6, 3s1. Or shorthand is I can just write, well, it's neon, and then it just has an extra 3s1 orbital. So you can just write the noble gas before it and then write the extra electrons after it. That's just shorthand notation. So let's see if you can fill in an orbital diagram for nitrogen. Pause the video, go back to previous slides if you need to, and come back when you have an answer. Alright, so nitrogen has 7 electrons. So 2 of my electrons will go in the lowest energy, 1s. 2 electrons will go in my second lowest energy, 2s. And then 3 electrons will go in 2p. So it will be 1s2, 2s2, 2px1, 2py1, 2pz1. Or you can just write 2p3. And if you draw out the boxes, it looks like this. Remember, these can be spin up or spin down. The important thing is that they're not paired yet because of Hund's rule. And that's it for this video. See you in the next one.